Okay, we're back, and this is the last video, but we're just going to do some homework problems here, some ones from lecture. So before we get started, what am I expecting you to be able to do? We're going to just outline exactly what I expect you to be able to do, and then we will go through a couple of these. I'm not going to do all of them that I had normally planned for class. This looks like a very simple equation, but there's actually a lot of work that you need to do this. So what I expect you to be able to do is I give you a chemical equation. I think this is a repeat from the last one. I'm sorry, kind of a gap in between here. Is use the tables and get a delta H. Is it positive or negative? And interpret all of that. Does that help it be spontaneous or not? Interpret all of that. Temperature is given to you, convert it to Kelvin. Calculate a delta S from the tables. Again, interpret it. Is it positive? Is it negative? Does it contribute to the spontaneity? Does it not? And making sure that you convert that to kilojoules. And your answer here will ultimately be kilojoules per mole. And then you can make a determination of, is the reaction spontaneous? How far does it lie to the right? Is it non-spontaneous? How far does it lie to the left? And do some comparisons there. We'll do some of those. And then the other equation is delta G equals minus RT natural log of K, and then the solved version of that for K and then be able to tie in equilibrium with the size of delta G and then go from there. Okay, so I'm going to go back to the slides, and we didn't do a ton of these examples. So what I'm going to do is actually do number one, but only for one of the examples. We'll just do the ammonia synthesis because it's pretty straightforward. And then I'm going to combine number two and number three, combining acid-base chemistry. And I'm not going to do the 50 degrees Celsius one for carbonic acid. I think you can do that one on your own. So we're doing sample calculations here. Fine. So sample calcs, which I think is actually officially the last slide of the semester. And I was having some technical issues earlier. I just want to make sure this is recording. Okay, it looks like it's recording. And again, I'm just going to do one of these that carries through this whole thing. Fine. And I'll add one little twist. So this is number one. Let's just keep looking at maybe you're sick of looking at this example. Okay. But I want to make sure that you interpret things step by step. Just don't blast through and get a number and not think about what it means along the way. So delta H here, under standard conditions, is pretty straightforward because it's 2 times the heat of formation of ammonia. So 2 times the heat of formation of ammonia. And make sure you look up ammonia gas. I think there might be ammonia aqueous in there. Minus, why am I doing this? Minus the heat of formation of hydrogen times 3, plus the heat of well, those are all zeros. If you look those up in a table, the heat of formation of something in its elemental state is 0. So if you know what you're doing, you can skip those. That's all 0, all of it. So the enthalpy of this reaction is just going to be 2 times the heat of formation of ammonia, which is off the table as kilojoules per mole. Okay, guys have to look that up. And I have my thermodynamic tables here. I have this as negative 45.9. So was that 91.8 negative? Is that right? I should know what it is in my head. So that's 90 plus 1.8. Okay, yeah, all right, fine. So that's exothermic. Again, make sure that you interpret this along the way, and that would help make the reaction more spontaneous because a negative delta G is what we're after if it's spontaneous, but not too worried about that right now. just be able to interpret it along the way. Delta S, just to exaggerate this. So it's 2 times the entropy of ammonia minus 3 times the entropy of hydrogen plus the entropy of nitrogen. None of these are 0, so you have to look them all up. And it's going to be 2 times and then 3 times plus. Okay, wait a minute, let's look up some numbers. Doesn't really matter what order we do them in. Nitrogen is 191.5. And that's joules over Kelvin times moles, so joules. Hydrogen is 130.6 joules over Kelvin times moles. And ammonia is 193 with no decimal places. That's kind of odd. So let's just take a minute, keeping in mind the minus sign, and calculate a value there. I think I can do this all in one slide here. 2 times 193 minus parentheses 3 times 130.6 plus 191.5 parentheses. I came up with negative 197.3. All right, and eventually we're going to want to combine these two variables, so I'm going to convert that to kilojoules. So that's going to be negative 0.1973 kilojoules over Kelvin times moles. Okay, again, interpret along the way. It is creating more order, which we expected, going from 4 moles of gas to 2 moles of gas. It should be a negative delta S. More order, less negative entropy. Sort that out in your head. Makes sense. Enthalpy, kind of hard to tell just by looking at it. So it's exothermic, and it's entropic. It's creating more order. Anentropic, not entropic, anentropic. Okay, another thing to take away from this is that the entropy value tends to be smaller in kilojoules than the enthalpy value. Entropy tends to be less important for spontaneity. Just tossing that out there. So boom, 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 we get that. Good. And we're going to do delta G. Now, I am not going to bother doing method 1 here. Method 1 is pretty easy for delta G, but that only works for 25 degrees Celsius. You just take 2 times the formula or the value from the table and do it like this. But I'm not really interested in that. I'm more interested in your understanding of this equation. So you can do it. We're using method 2 for the equation. And we'll try 2 different temperatures here. Incidentally, this is the manufacturing temperature. We're going to get a weird answer, but I don't really worry about that. I just want to do 2 examples side by side. So delta G at 25 degrees Celsius. So delta G equals delta H. Make sure check our units here. Negative 91.8 kilojoules per mole. Go ahead and just rocket ahead if you want to do this. Minus T, which is going to be 298 Kelvin, don't forget that. And then delta S is negative 1973 kilojoules per Kelvin mole, or mole Kelvin, it doesn't matter, and the units cancel there. And whenever you add or subtract two numbers, they have to have the same units, so kilojoules per mole, that'll work. So delta H minus T delta S, and I'm going to set this one up. Celsius should be 723 Kelvin. Let me double check that. Yeah. Again, just to agree, because that's to be Kelvin mole or mole Kelvin in the denominator. It still cancels and leaves you with kilojoules per mole. So that's the math for both of those. And let's just solve. And it's always negative times a negative, so I'm not going to bother. I'm just going to make that a positive. Negative 91.8 plus those two things times it, so times 298 times 0.1973. Okay, and I came up with something looks strange there. Did I do that right? Okay, so I go with negative 33. So that's saying it's pretty spontaneous. You're going to get kind of a quirky answer over here. It's, okay, so plus 723 times 0.1973. Okay, it's a good problem. Excuse me. This doesn't have a whole lot of basis in the real world, but because we use catalysis and we use pressure to make the reaction go, but I'm not too worried about that. We're just looking at temperature. So what does this tell us? That tells us that at 25 degrees Celsius, this reaction is spontaneous. At 450 degrees Celsius, this reaction is not spontaneous, which is a very strange thing. We jack the temperature up and it becomes less spontaneous. Well, that can happen, but again, this is just an example. It's not a great one, but it's easy to interpret. And finally, just so we have it, we wouldn't really want to do it in this case, but we could calculate the delta G. Okay, well, or the K. You know what? I'm not going to bother with that. We could, well, maybe we will, just to round it out. It's not going to tell us anything new, but let's just do the math. So non-spontaneous, spontaneous, okay. So this should have a pretty large equilibrium constant. This should have a pretty small equilibrium constant, but let's just do it. So to get the equilibrium constant, we would take, oh yeah, I do want to do this for one reason. R is 8.314 joules per Kelvin mole. So we set this up, one of these has to be kilojoules. It doesn't matter to me which one you do. I always like to trade this and make it back into joules. It's easier in my head. So K is going to be equal to E all raised to the negative, oh geez, times the negative, and this is going to be 3.3 times 10 to the 4th joules per mole. Yeah, it's negative. Divided by RT, yikes. I guess I'm going to use brackets here. So there's divided by 8.314 joules per Kelvin mole times T, right? Yeah, 298 Kelvin. So those should actually, I didn't set that up very well, but those two should be in the denominator of this one, and it's going to be a positive value. I'm just going to set this up. This is going to be e to the positive, let me just get a number in there. That's not the final answer we're going to get, but let's just make sure we get it right. So, negative times a negative is a positive, so we get rid of that. So this is 3.3 exponential 4th divided by parenthesis 8.314 times 298, 13.3. So I came up with e to the 13.3 power, but you don't leave it like that. So exponential 13.3. Okay, we get a huge equilibrium constant, 5.97 times 10 to the 5th. And I'm going to double check all of this. Yep, e to the 13.3. I'm just going to check the video again. Like I said, I had some problems earlier. Seems to be working fine now. So exponential 13.3. Yeah, 5. So 1, 2, 3, 5. 5.97 times 10 to the 5th. So it's a large equilibrium constant, which is synonymous with a negative delta G. Spontaneous lies heavily to the right. Products are favored in this case. So that would be an analysis that I expect you to be able to go through. Just for comparison's sake, this is going to be, K is going to be equal to e to the, well, let's just cut to the chase. And e is going to be, it's going to be raised to a negative power, right? Because it's, yeah, negative delta G over RT. The delta G here is positive. So anyway, so this is going to be e to the negative something or other. So we're going to take 5.08 times 10 to the 4th, so 5.08 E4 divided by parentheses R 8.314 times T, which is not 298, it's 723. I get e to the negative 8.45, which I'll leave it like that as usual. And let me just double check it. 5.08 E4 divided by. Yeah, okay. So e to the negative 8.45. And I got 2.14 times 10 to the negative 1, 2, 3, 2.14 times 10 to the negative 4. Again, small equilibrium constant, consistent with a non-spontaneous free energy. Be able to interpret all of that. So those are good. That's a very comprehensive example going through all of this math. So I'll put one like that on your final, no doubt about it, but I think you can handle it. And the last one I want to do for the semester here is on the slides, is to combine number 2 and number 3. I think it's going to get to be busy work with this video. Nobody's going to watch it because you won't need it. and it won't be nearly as long as this one because I think you can do this, is carbonic acid. While you're waiting for me to fumble around here, go look up the two Ka values for carbonic acid. It's a weak diprotic acid. We've done it before. Just go look those up so that you have them. And those are equilibrium constants. You could get delta G, couldn't you? So I'm combining examples 2 and 3 because these are good examples to finish on. Okay, so you're given the information that carbonic acid is weak, it's diprotic, so we have 2 equilibria that we have to deal with. And I am going to write AQ on everything because when you look this stuff up in a table, it matters that it's AQ, or solid, or gas, or liquid. And let's keep it simple. So it's diprotic. So that will be the first equilibrium. Carbonic acid giving up one of its H pluses, protons or hydronium ions, leaving you with bicarbonate, excuse me, and then that bicarbonate will then be in equilibrium with the second proton, leaving you with carbonate. All of this stuff should appear on the thermodynamic tables, all of it. So you should be able to get a delta H, a delta S, a delta G if I tell you the temperature, and do all of that math. So I'm just going to kind of catalog that for you here. You should be able to do that. I'm not going to do it, but you should be able to. You should be able to get your delta H. You should be able to get a delta S. You should be able to combine those two at a certain temperature and get a delta G. Kilojoules, that ends up being joules divided by 1,000. Okay, do all of that and get that delta G, and then calculate, in this case, the equilibrium constant is not generic equilibrium constant, it's the Ka. So if you need the practice, go ahead and do that for these. Everything's 1-to-1, it's pretty easy to do. I think I have these written correctly. Great. And then I think the temperature I have you do these at for number 3 is 50 degrees Celsius. That's actually not a bad problem, but I'm not going to do it with you, okay? The tables give you the Kas at 25 degrees Celsius. When you do this calculation, it asks you to do them at 50 degrees Celsius. Would the Kas be greater than that, less than that, or unchanged? That's a good problem actually to take a look at, but I'm not going to do that one here. So what I just want to do is an example of the calculation we haven't done in the interpretation. So remember, this is called Ka1, this is Ka2. And all we're going to do here is calculate the delta G's. I'm kind of bouncing between number 1 and number 2 here. Okay, so this is actually a pretty easy calculation. Let's just look up the Ka values. Did you find them? So Ka1 is 4.3 times 10 to the minus 7th. Ka2 is 4.7 times 10 to the minus 11th. And the calculation here, we already know the equation. So delta G for the first equilibrium and the second equilibrium, and we're just doing these at 25 degrees Celsius, it's going to be negative RT, natural log of K. Let's see here, so it's negative 8.314 joules over Kelvin mole times 298 Kelvin. Let's again remember the equation. Delta G equals minus RT natural log K. You'll have that equation available to you. It's the same for both. And we'll just put an equilibrium constant. Again, I'm going to check the camera because I really was having trouble before. Okay, sorry for all the back and forth. And all we're going to do is put in our equilibrium constants and see if that makes sense. So, the first equilibrium constant, and we don't really, oops, I'm sorry, I forgot the natural log, didn't I? Minus RT natural log of K. 4.3 times 10 to the minus 7th. So make sure you do the natural log of 4.3 times 10 to the minus 7th, and the natural log of 4.7 times 10 to the minus 11th. Whew. It's our last problem of the semester. I'm kind of excited. And let's just see what we get. So, negative 8.314 times 298 times natural log of 4.3 exponential negative 7. And I came up with a huge number. What's up with that? Well, because the units are going to be, Kelvin cancels, that's unitless, no units there. So the units here are going to be joules per mole. So you get a huge number. You get, I came up with a positive number, positive 3.5 times 10 to the 4th joules per mole. But we don't report free energy in joules, we report it in kilojoules. So this is positive 35 kilojoules per mole. And this one ends up being you can get the answer, positive 59, depending how you're rounding, I guess. Yeah, that's 59 kilojoules per mole. Again, the math is fine, but these are weak acids, very weak acids. What does that mean? That means that the reactants are favored because the equilibrium constants are so small, which means they're not very spontaneous. That was a whole bunch I just said right there. But those are the concepts we want you to connect together. Equilibrium, if it's a small equilibrium constant, it's not very spontaneous, and this shows that. It's really the same thing. It gets less spontaneous as the equilibrium constant gets smaller. So that's really where we're going to end here. That should let you do the homework. I just checked this. So the final homework of the semester should now be in your wheelhouse, and some of these problems will definitely be emphasized on the final exam. And that's it, folks. So I'll see you online, and that's it for videos for the semester. Hopefully that's a good thing for you. It's been good. I'm glad we had this facility here to do this. I think it really helped out and went pretty well. Okay, take care.